Imagine you are standing on the edge of a deep water pier, looking down into the dark, churning surface of the ocean. Below that surface lies a world of crushing pressure, zero visibility, and freezing temperatures. Every bridge pylon, every offshore oil rig, and every transatlantic cable sitting on the seafloor is a miracle of engineering. To build on land is to work with the elements. To build underwater is to wage a constant war against them. The first and greatest challenge of underwater construction is a simple, fundamental problem. How do you get the water out of the way? You can't pour concrete into a wave. And you can't weld in a flood. The oldest and most effective solution is the cofferdam. Imagine driving giant steel sheets into the seabed to form a watertight circle, then pumping all the water out of the center. Suddenly, you have a dry hole in the middle of the ocean. Engineers can walk on the seafloor, wearing standard boots and hard hats, building massive foundations as if they were on dry land. But as you go deeper, the pressure against those steel walls becomes immense. If a cofferdam fails, it doesn't just leak, it implodes with the force of a bomb. When the water is too deep for a cofferdam, we use caissons. These are enormous, hollow structures, often the size of a multi-story building, made of concrete or steel. They are constructed on land, floated out to the site, and then sunk to the bottom. For pneumatic caissons, workers actually go inside the hollow chamber at the bottom of the sea. The chamber is filled with high-pressure air to keep the water out. In the 19th century, men built the foundations of the Brooklyn Bridge this way, working in the dry, while the river flowed above them. But this came with a terrible price. When they returned to the surface too quickly, the nitrogen in their blood formed bubbles, leading to the agonizing and often fatal condition we now know as the bends. Today, the heavy lifting of the deep is done by a specialized elite, the commercial saturation diver. These aren't your weekend scuba divers. They live for weeks at a time in pressurized chambers on the surface, their bodies fully adjusted to the pressure of the depth where they are working. They are ferried down in diving bells to perform tasks that robots simply can't handle yet. Tightening massive bolts, inspecting welds, and navigating the complex tangle of subsea infrastructure. They breathe a mixture of helium and oxygen that makes their voices sound like cartoons. But their work is some of the most dangerous and technically demanding on the planet. But even the bravest divers have limits. For the truly deep work, thousands of feet below the surface, we turn to ROVs, or remotely operated vehicles. These are the drones of the deep, controlled by pilots in comfortable chairs on a surface ship. These robots are equipped with high-definition cameras and hydraulic arms capable of surgical precision. They can stay submerged for months, performing maintenance on oil wells and laying fiber optic cables that connect the global internet. Without these mechanical explorers, our modern digital world would literally sink. Then there is the chemistry of the water itself. Saltwater is a corrosive acid that eats through standard steel and degrades normal concrete. To build for the long term, we use Tremy concrete. This is a special mix that is pumped through a long pipe directly into the underwater forms. It is designed to be self-compacting and water-resistant, displacing the seawater as it rises. We also use sacrificial anodes, blocks of zinc attached to steel structures. The saltwater attacks the zinc first, leaving the structural steel untouched. We are essentially giving the ocean something else to eat, so it leaves our bridges alone. One of the most incredible feats of underwater construction is the immersed tube. Instead of digging a tunnel under the seabed, we build the tunnel in giant segments on land. We seal the ends, float them out, and sink them into a trench on the ocean floor. Divers and ROVs guide them together with millimeter precision. Once they are bolted together, the water is pumped out, and you have a highway under the sea. Why do we do this? Why face the pressure, the darkness, and the salt? Because the ocean is the final frontier of our infrastructure. It holds the energy we need, the cables that carry our thoughts, and the paths that connect our continents. Underwater construction is the ultimate testament to human stubbornness. It is our way of saying that even the deepest, most hostile environment on our planet cannot stop us from building. The next time you drive over a massive bridge or look out at the horizon and see a distant oil platform, think about what is beneath the waves. Think about the concrete poured in the dark, the divers living in pressure cookers, and the robots navigating the abyss. We have learned to build in the sky, and we have learned to build in the dirt. But our greatest triumph might be the silent, massive monuments we've placed at the bottom of the sea. As you look out over the ocean, do you see a barrier that separates the world